I'm happy you're still here. Last day. Uh, I'm happy you're still here in the last day. Not that it's the last day, but. um, right. So today I want to do more like what I started in the last minutes of the last lecture, which is talk about maybe quantum circuits and circuit complexity and so on. More about like computation maybe than entanglement. But in the end, I think we have to connect them in some way at least. So is there any question from last time before I continue? Right. So we had this motivation from black hole, which we know there was this final thing, right? This Harlow-Hayden, which is was like there is this violation of monogamy of entanglement, which can be seen as a violation of unitarity in mechanics. But to have this thought experiment where you can, where Alice could observe this violation, she would have to decode this Hawking radiation, right? Meaning you have to apply this unitary, which it exists, which is a unitary on the early Hawking radiation and on the Hawking radiation that just left, which would write this big unitary, which would map into a maximum entangled state of the the most recent Hawking radiation with another particle and something else that we don't care. And then they claim, well, maybe it takes a long time to apply this unitary. And in particular, once you apply this unitary, it takes such a long time that they evaporate. So you never have access to the three systems at the same time, right? And therefore, black hole complementarity holds, right? So you're fine. Then the question emerges, right? What it means takes a long time to apply this unitary, right? So this might depend on some detail of physics, or this is some intrinsic property of the unitary. Is there a way to quantify that, right? And then I start talking about this circuit model, right? So the circuit model is just is a model of computation, and we think a good model for whatever we can compute efficiently in the universe, right? Which was the content of this quantum Church-Turing thesis. So what was the model? The model is that we have qubits, n qubits here, for example. I can use this diagram, and then it's just starting each time use two qubits, and you apply a gate here. We call quantum gate, which is a 2-qubit unitary matrix, right? So you do identity here, and you apply this 2-qubit unitary matrix, and then you do that, and so on, right? And then you can form some big unitary on n qubits, right? Which is the product of the smaller ones. Good. So this is the set of unitaries of dimension 2 to the n, right? So it's a set of all unitaries on n qubits. And here I'm saying that you have a special one, right? So this unitary is special in the sense that it can be decomposed like that. So now we can just start studying, okay, composition, what is the structure, right? So that's one question. So one thing, some things you can show. I won't prove this to you, but suppose we choose all V in the set, okay? Or in another way, given a V in this set, there always exists a circuit, okay? Like these are 2-qubit gates, right? V1, Vn, but n is very big, n is exponential. I think 4 to the n is enough, such that you can write as a circuit. Okay, so far we didn't lose generalities, right? The fact that we can break into these smaller unitaries, actually you can write any unitary in form, but using a huge number of them, right? Using exponentially many of them. Yes. Oh, sorry. Yeah. Yeah. That would be. Yeah. What would the value of n? I don't know. Yeah, little n. Right. So if you allow this is the size of the circuit, right? We call it the size of circuit, of quantum circuit. So if you allow circuits of exponentially long time, with exponentially long number of gates, qubits, then any dynamics in quantum mechanics can be written like that, right? But now, the idea of efficient computation, right? So we say, which is when n is not too big, right? N is positive in n, in small n. And this is the class of unitaries we like to understand. So, so what was the example we saw last time? Example, if you just have something like this, where H is a local Hamiltonian, then you can always approximate this with the error epsilon by a quantum circuit with n like that, right? So in particular, you know, this good, like you can think on the fundamental level in physics, you just have these local Hamiltonians, right? Like, I don't know, Hamiltonian of the standard model or something else. And indeed what we can do is dynamics under them. So it's good that they have a polynomial quantum circuit, right? Yes?
What's the assumption about VI to V1 to Vn? I mean, V cannot be one of these.
Oh, sorry, because yeah, I should write this. So each one of these VI is a unitary acting only on 2 qubits. So it's element of U4, right? Right. So right, think about it. It was one of these boxes, right? So it can only is a Hamiltonian, some time evolution of Hamiltonian only on 2 qubits, and on the rest you do nothing, right? So it's this idea of computation, right? We want to break some big operation on n qubits into a sequence of smaller operation where each one of them only acts on, right, a few qubits, and can be 2, for example. Great. So, you know, in a way, the idea of quantum computation is just that, of finding quantum algorithms, for example, is just that you have a problem you want to solve, right? There is some unitary that solves the problem. For example, can just be the mapping from input to output. Right, there's some, and you want to find whether there is a decomposition of this unitary into smaller blocks where this n is not too big, right? That's like one way to think about algorithms, right? For example, yeah. So there are many, yeah. So it could be just this guy where each one of these acts non-trivially only on a few of the qubits, right? So it can be very non-local in the sense that it doesn't drop off exponentially, but like few body, right? So each one of these like acts non-trivially on other one qubits, right? Or other one, yeah. Right. So good. Now we can ask a question, right? So what is the size of this set, right? So how the set of quantum circuits, of efficient quantum circuits, so quantum circuits of small size, compares to the set of all unitaries, right, on n qubits. Are they the same? Maybe they're close, right? So, and what do you think will be the answer? Will be very small, right? Why do you think so? Right, it should be hard, right? Yeah, that's true. So let's do one easy way to see that. Let's count. Let's do some parameter counting, right? So let's see how many unitaries we have of this form, just like the leading scale, right? So the unitary has 4 to the n parameters, more or less, right? So that's the number of unitaries. So that's the number of parameters in this matrix, roughly. But okay, so the number of parameters in to specify, right? Yeah, but I will be very. You see, there won't be a difference because I'm going to. I don't care about the exponent so much, but yeah, it can be real parameters. Let's just write as 2 to the order n, right? And then this means that suppose there's a precise way of doing that, but now this means that how many different unitaries you can have, for each of these parameters, right? You have, well, actually many choices for them because it's real number, but let's just discretize. So let's just suppose you have like a finite number of different values for each entry of this. So the total number of, the number of like of elements. Yeah, let me write coarse grain because like of coarse graining elements. Right, because of course this is a continuous group, so you can say there are infinitely many unitaries, right? But you say I don't care, right? So you have this unitary group, okay? There are infinitely many unitaries there, but now you can put what we call epsilon net, right? So this we have to see this concept. Epsilon net is just a covering. You have unitaries here, okay? You have unitary here, and you have the promise that for any other unitary, it's epsilon close to at least one of the elements in the set, okay? And now basically, if you want to have a covering, a epsilon net here, we will need a number of so the size of a epsilon net for u 2 to the n, this will scale as double exponential n. This will be something like 2 to the other n. Okay, just think about, because roughly that's the rough intuition. I'm going to show you how to get this more precisely soon, but now that's just the rough idea. So we have this epsilon net, and a way to think of that is that for each entry of the unitary, we have two choices or three choices, like a finite number of choices there. But then for each one of them, suppose you have two choices. So for each entry, you have two choices, and you have 2 to the n entries, right? So the total number of different choices is 2 to the n. So very big set, right? On the other hand, what is the size of the circuits, quantum circuits, of with size, but now the size of the circle with size n, right? Meaning that there are n different gates. So who knows how this should scale? Imagine counting again, right? So for each gate, right, we have n different gates. Each one is a finite number of different options there, right? So it's some constants, and then in each case you have this finite different number of choices. So in the end, we have something exponential in capital N, right? So this will go as 2 to the order capital N. Okay. So if we want the parameters to match, right? The only way these two parameters can match is if capital N is exponentially big in n, right? Which is what I mentioned before there anyway. But now for efficient quantum circuit, right? For efficient circuit, this epsilon, n should scale as polynomial small n, right? And therefore we have these two very big numbers, right? So we have 2 to the order n. That's the number of different unitaries you can have once you put this epsilon net, not to count things that are very close to each other, versus 2 to the poly n. Okay, so this is like much smaller, right? So you have the set of all unitaries here, right? You have un, u2 to the n, and a tiny, tiny set here, right? There will be like efficient computation, right? Okay. And sometimes this is called like the illusion of the Hilbert space, right? Why so? Well, because we learned quantum mechanics, any unitary can be implemented, right? Great. We can always find some Hamiltonian that we could implement in principle. But now you see that when you start growing the number of qubits, the size of the volume of the system, then doesn't really make sense, right? So the vast majority of unitaries, we will never see them in nature, right? Because they are just too complicated physical process, right? So if you believe that whatever we can see in the universe is just efficient quantum computation, right? And that's basically this quantum strong Turing physics, then all these unitaries here in the wild, right, or very high complexity, they're completely irrelevant, right? We'll never find them. We can never implement them. We never see any physical process described by them, right? So even though great quantum mechanics described by Hilbert space, and right there is linearity there, and there is any unitary in principle we can implement, is not really true, right? What we care about is a tiny subset of quantum mechanics, right? Where we have to put the constraints from quantum mechanics that we learn when we learn quantum mechanics and something else, right? We need some information about locality of physics and so on, right? And this puts us on this corner here. So yeah. Well, usually the way we put this restriction on physics is that we care about specific Hamiltonians, right? And therefore this is imposed by the Hamiltonian. For example, by the Hamiltonian being local, right? So every Hamiltonian we encounter in physics is local, and therefore we are already there in that corner, right? Yeah, that's right. There's a similar idea. So you can do the same thing for quantum states, right? And actually, I'm going to do just now for quantum states the same picture, but there's a result. We can do it more precisely. That's why I want to do it. And there is the same. Indeed, the vast majority of quantum states, they have exponential circuit complexity, so they are just meaningless. We never see them. And there's a tiny corner, and this tiny corner, for example, okay, there's a tiny corner which is like what you can create by a quantum computer. There is even a smaller corner, which is what tensor networks represent well, right? And then yeah, and we want to understand where, which states are in each one of these two corners. Yeah, they change very little, right? Because what you can do is apply unitary here and here, right? A way to apply it, you just apply 2-qubit gate, which is the swap gate. You swap this with this, then this with this, then this with this. You apply, right, the original one here, and you swap back. So it means that, right, whenever you have a non-local one, you can change it by order n, right, where n is the number of qubits, nearest neighbor one. So there is this factor of n, but it doesn't change, right, a polynomial to exponential, right? Then as long as, right, so then you can use this result, right? Because suppose you have a unitary acting on k qubits, let me call like uk. Then we know, right, that this can be again decomposed as a circuit of 2-qubit gates, where this n is exponential k, right? So as long as k is a constant, or if you're happy. So there's all these robust things, but it has to be, you can touch any qubits you want, but a constant number of them, and then it's a model. Good. Yeah. Yeah.
While we were trying to construct, the black hole is always leaking some more Hawking radiation, right?
Right.
So our
Well, okay. I didn't want to go back. Let me go back very quickly to there, but yeah, it won't take. It's maybe it's good just to have as a motivation for this, right? But so sure. No, it's a physics. That's why it's something you cannot. It's a physics, right? So meaning that it's not something you can prove. It's something that we can gather evidence for it, right? And as far as we know, we have So we are gathering evidence, but there was a lot of evidence before quantum computation too for the other one, right? Which was refuted by quantum, at least, right? So, but for example, each time more we know any local Hamiltonian, right, can be simulated by a quantum computer. So that's an indication for it, right? Then we know a lot of people study quantum field theory, and they show they still can be, right, with all the regularization and so on they have to take care of, can be written in this form too. And now, I don't know, the ultimate goal would be quantum gravity, right? First we have to have a theory of quantum gravity to do that, but right, so that's the goal, right? But indeed, it's a physics, so it's not something that we have a proof. But just to remind you, right? We had this H, we had this B, we have this inside the black hole. Hawking radiation just left R. And the idea was that if it's an old black hole, there is a unitary which can be applied here, right? Which maps this to B being in a maximally entangled state with some RB, right? And some other system that we call RH, which is maximally entangled with the black hole. It doesn't matter, right? So that was the goal, right? To extract this guy, right? Then Alice could jump in, and there was like a B prime here, which also be maximally entangled. That's a problem, right? Now you're saying, okay, when they're applying this, there are more Hawking radiations leaving, right? But we don't care because we just count this as part of H, right? No, just some part of H is outside, but that's okay, right? Now what is here really that if it takes so long to apply this U, that after you apply it to get this guy, then everything left already, right? Then then you cannot access this B prime anymore, right? This B prime already reached the singularity and disappeared, right? So, yeah, relevant, right? If the circuit complex is big or not. Okay. Show you something in this direction of unitaries. It's true for unitaries too, but I want to show you for states because there is a cleaner formulation about again how most quantum states, they are not really meaningful. They are just some abstraction. So yes. Uh-huh.
Now we're discovering that we have the theory,
Yeah.
quantum mechanics,
Yeah.
describes reality, and
Yeah.
now we start to see that there are states that are really not physical.
That's right.
It's as if there's an axiom missing in the theory of quantum mechanics. Also,
Yeah.
take some axioms that you have plus
Yeah.
assuming computational complexity efficiency or something like
Yeah. But I think that's right. But I think implicit, that's what I said before. Implicit people have been doing that just by considering local Hamiltonians, right? Which is kind of just equivalent to say, right, like circuit efficient quantum computation, right? So indeed, it's hidden there, but yeah. Right. So you say maybe there is a simpler description of quantum mechanics, right? Yeah. So for quantum computation it doesn't really work, but if you have this restriction of like area laws and so on, like this is where tensor networks enters, right? So the quantum state, instead of thinking about a quantum state as this vector in the Hilbert space, you think in terms of this local structure of the tensors, right? So that direction, right, is a different parameterization, which is more effective for numerics, right? For classical numerics, for example, right? So that goes in this direction. No, so this class of the states, they can be generated by quantum circuits, more general than by tensor networks, right? So most of them tensor network effect. Okay, but let's look at for a while, right? So let's and make a definition first. So the circuit complexity of a unitary V we define, which we call Cu maybe, and maybe some epsilon because we only do it approximately, maybe is the minimum n such that there exists a quantum circuit Vi 1 to n such that how do I write it such that okay. This is true, and this is the operator norm. Operator norm is just a way of measuring if two unitaries are the same. So operator norm of x is just square root lambda max eigenvalue of x dagger x. Okay, so as we had the trace norm for states, the right thing for unitaries, well, a good thing for unitaries is the operator norm. There is bad other ways like diamond norm is called sometimes. It's more relevant, but that's good enough for us. Right, so it's just, you know, a unitary might be many decompositions in terms of local gates. We want to find the shortest one, right? And that's the most efficient way of implementing the unitary, at least approximately, up to some error. Usually we are fine, right? If there is some small error. And then there's a problem given this. Completely possible, right? So like very, very, very hard, right? So there is no genre of computing it. But it's still something you can define, right? And what I hand my waves to explain here, right? You can show if you want. We will show for states now, but for almost every unitary, the circuit complexity will be exponential. Okay? So most of them are very hard to implement. That's what I said in words, right? It's not measure zero, but I'd say suppose we will look at the Ha measure here, the uniform measure on all unitaries. Okay, it makes sense as well. We can define. You pick a unitary at random. The probability that it doesn't have the circuit complexity is doubly exponentially small in n. So it's not measure zero, but it's very, very, very tight. Yeah. And now we're going to see why this is true for states. Okay, so actually this will be this result, right? Suppose we define the same notion for states, right? So this is circuit complexity of a unitary. So do I have to write again? Maybe. So the circuit complexity, but it's the same thing. Of I say psi. Let's use just this for simplicity. So right, so it's the same thing. We start from the all zero state, it's like zero everywhere, right? In the computational basis. We apply the circuits, and we want to have a good approximation of our states. Right? And that's the circuit complexity of it. And now we have exactly the same statement, okay? And we have something stronger, that's what I want to show you, which is interesting. And I want to do that states because there is another one of these like useful results that we use a lot in quantum computing and actually quantum information theory as well, which is just exploring this equivalence of quantum states with points in this higher dimensional sphere, right, that we saw before. So we can explore something they call a measure concentration there, which is a phenomenon in high dimensional geometry, which says that any continuous function, so basically any function that has like a Lipschitz constant, it will be almost constant throughout this higher dimension sphere. And the higher the dimension of the sphere, the more constant it will look like. Which is kind of counterintuitive, so it's nice. It's called Levy's lemma. It says the following: suppose you have function, okay, and it goes from, let me call this the how can I, let me call this the sphere on m dimensions, okay. Is a function from a point at the sphere of m dimensions to the reals, and this f is eta Lipschitz, right? Meaning that's the case, right? For all x and z. Then let's look at the probability over x, which is taken at random, completely uniform from the sphere. The probability that f of x deviates from the average. This is the average of f over all the sphere, right? So imagine it's like a big sphere, and we have points here, right? And we compute a function on this sphere. The probability that this is bigger than epsilon, that's very small. So that's 2 to the minus, there's some constant, c, epsilon square, m, divided by eta square. Okay? But now, this directly translates to properties of quantum states, right? Because quantum states are just points in this sphere, but if you have n qubits, right, then this m will be 2 to the n, right? So now we have like, right, so, but before that, is that clear? Is there a question about this statement? It's just like a math statement, right, which is very interesting, right? So this is what I say, it's almost constant, right? So almost everywhere, there is like a exponentially small probability if eta is not very small, right? Suppose eta is a constant, the Lipschitz constant. There is only exponentially small probability in the dimension of the sphere that, you know, the value of the function at some point x deviates from the average by more than epsilon, right? So almost everywhere it has to be epsilon close to the average, right? Sorry? Eta shouldn't be very big, yeah, right? The bigger, right? The smaller is the decay, yes. Okay, but why do I tell you that? So let's apply this to quantum states. So by Levy's lemma, right? Let's take the probability over a random state now. Okay, from the Haar measure on C 2 to the n. And let's just take, that will be the function. The function will be, we have a observable m, like some p of m, maybe element m, right? M is a p of m element, and we look at the expectation value of this m on psi. And then we compare that with the, right, so this is our f, okay? So this is f of psi. And we want to apply that result, so we have to take the average. But the average over all states from the Haar measure is easy, right? We just replace this by maximum mixed state, right? So here I have trace m 2 to the n. Yes? That's right. That's right. Yes.
It's really equivalent to the Haar.
Is the Haar measure for, if you think, yeah, right. Now we want the probability that this is bigger than epsilon. And by Levy's lemma, that's smaller than 2 to the minus c epsilon square 2 to the n. So double exponential is more in n. What is the Lipschitz constant of this? So we just change the constant. I'll let you show that. So right, so show that for this f, right? So basically, want to show that. Well, there is a substitute here, but let me mention. But for this f, That's actually for that result, the norm here is not like trace norm of states that we saw before. It's actually the Euclidean norm of these two vectors, right? They're vectors. There's the Euclidean norm. That's here, but you can show this. Leave you to check it. It's easy. So we find it, right? So we get that for this fixed measurement, almost every state has expectation value really similar to the maximally mixed states, right? But now we can go beyond. Now we can do it's called like union bound. So well, before that, let's now actually consider the following problem. Let's consider a set of POVM elements of measurements, right? I from 1 to n, okay? And now let's look at what is the probability that any of them gives an expectation value on psi substantially bigger or different than the maximum states. So in other words, I want to look at the probability over psi r of a maximum over I from 1 to n of this thing being bigger than epsilon. Okay, I care about this probability now. Sorry, so yeah, exactly, right? So so now we want that psi looks like maximally not with respect to one measure m, but with respect to a set of measurements, okay? And now, because this is so we have something about this too, and that's union bound. That's what you do. So this thing, okay, what you can show is that this is always smaller than n times the original probability, the probability over psi, and it's called union bound. I'll explain how we use it, but the probability, well, sorry, actually, the sum. Right, and once we use that, we get n to the n. Okay. Why this kind of union bound? Well, this is the probability that there exists. Right, there are many events. Each event for the particular I, this quantity is bigger than epsilon. Okay. And here, what we are doing? Here we are doing the probability of the ORs of this event, right? We want, because the max, we want or with M2 is true, or with M3 is true, or and so on, right? If for any of them is true, then we are happy, because we're taking the maximum. But then this probability is always smaller, right, than just the sum of the probabilities that one of them is true, plus the sum of the other is true, and so on. Right, so it's just this base effect, it's called union bound, but then we get this. So maybe it was lost already, and you don't know why I'm doing that, but now I can tell you why. This is very strong now, saying that doesn't matter how you choose these POVM elements, if the cardinality of them is not too big, if it's n, then this, right, so as long as the cardinality let's set is smaller than basically this double exponentially thing, right? As long as it's smaller than that, then a generic, right, a psi from the Haar measure looks like the maximally mixed states. With respect to the set of measurements, right? Meaning that if you measure any of these measurements, you cannot distinguish the two states, right? With respect to the set Mi.
You will need like to perform lots of measurements, a big number of measurements to distinguish.
No, it's even stronger. It means that doesn't matter which of these POVM you implement from this set, the bias that you get from maximally to the true state is always, right, smaller than epsilon, and epsilon can be something exponentially small in n, right? Think about epsilon can even be like something 2 to the n over 4, right? That's still enough, right? You only have a exponentially small probability of distinguish any of these states from the maximally mixed states using any measurement in this set. And because the bias is so small, it just means they're really the same state. You never see a difference between them, right? Is that clear? Okay, great, but now this set can be anything, right? This set is anything. Let's just look at the set of all measurements which you can implement efficiently, right? So, which is basically all set of measures that we care about, right? Yes. A POVM element, I'm defining this, right? This is a measurement we can implement, right? And each one of those defines a measurement you could do, right? Because you only want to distinguish two states, that's with the laws of generality you can assume is a two outcome, right? POVM. Okay, but now let's this let's take as so take this as set efficient or efficient measurements, meaning all measurements for which we can implement them by add ancilla, apply a polynomial time quantum circuit, measure in the computational basis some of the qubits in the end, right? Basically any measure that you can implement in reasonable time. So these are the sets, and the question is what is n in that case? Well, n in that case, right, so each measurement is specified by the quantum circuit that we apply there, right? So you have, you know, again, so you want to apply the measurement to some particle, you add some qubits as ancilla, you apply a big efficient quantum circuit there, and you measure some of them. So the number of parameters really is the same as the number of parameters of quantum circuits, right? That we saw before, right? We saw that they go like exponential in some polynomial in small n, right? The number of qubits, right? So putting together, we see, right, this is much, much bigger, right? So the conclusion, almost every quantum state looks like maximally mixed with respect to any efficient quantum computation. Mixed for efficient computation. Okay, so what this means? Well, it means they are, right, they are abstraction, right? We don't really, first, probably they do not exist in nature, these states, because if they would exist, well, it would take a very long time to construct them by any physical process, right? So there's no time. And even if they were there around, we could never tell if they are really there or if it's just some thermal state that's infinite temperature, right? Because that's just the maximally mix. So yeah, I think that's kind of striking thing, right, about this like this very large dimension of the Hilbert space. Okay. Yes. That's right. If you only have access to efficient quantum computation, yes. That's right. Yeah. Correct. Yes. That's what it's saying. Yeah. Um, and then, yeah. And then you, well, it's they can say, well, yeah, that's a strong, very weird thing, right? Whether something like that. Okay, the way out is just to say this never, right? They're just not relevant. These states, we should forget about them. But then you should start complaining that, for example, the way I model a black hole, say there was a random states, right? And maybe there was a bad approximation then, right? And there's answers to this, but let me. I just want to tell you one thing. Which is that actually an idea not as strong as but on the same direction actually is at the core of what we understand in the moment of like quantum chaos. Okay, so connection like to statistical mechanics that I wanted to make, I didn't have time before, so maybe that now is a good time. And in particular it's what we call Eigenstates Thermalization hypothesis. So the idea here is that suppose we take a Hamiltonian, now a local Hamiltonian, okay? Some local terms. For example, it could be what is maybe chaotic in one dimension, like you have some spins. I is interaction, but then you have a magnetic field, and you have X interaction. Okay, Hamiltonian. What I'm going to say applies for this, but we think almost to a very large class of, actually almost every, apart from some set that we try to understand when there is localization. Then what this says something similar to this, but for a weaker model of computation, if you want. It says that we say that H satisfies ETH if we look at the eigenstates, the eigenvalue decomposition. Okay. And now suppose, you know, this result saying that almost every quantum state looks like maximum mix when the measurements is a set of efficient implementable quantum measurements, right? Now look at another set of measurements, namely the set of local measurements. Okay. So now there is the line here if it's a one-dimensional model, and just a set of measurements which involve just a few spins, nearby spins, right? Then satisfy ETH if for all observables M, which is local, so M only acts on, or maybe for all, let me just state for all local observables M, Um, the expectation value here of a particular eigenstate will be very close to the expectation value of the thermal states of the Hamiltonian with respect to same observable, where beta is such that the temperature is such that energy is conserved. So basically, beta is given by this equation. Okay. So first, why I mentioned that, that's very similar, right? It's saying that there's a set of measurements, but not a set of measurements instead of all efficient implemented quantum measurements, a set of local measurements. And you say for this class of models, many body models, this quantum states, now the eigenstates, right? So now an initial for every eigenstate, ETH says, locally, it looks just like the maximally mixed states, but now, right, because there is energy, we have to look at the thermal state, right? You could also consider microcanonical state in some energy shell would be the same, right? So we believe that's true for almost every model, right? So it's very hard to prove. There is numerics, people can do numerics and so on. It's something very interesting, right? It says that in quantum mechanics, equilibration happens at the level of eigenstates already, right? Very different from classical, right? And it does, and it's important because it helps us to understand in quantum systems, right? So ETH, if you assume ETH, then indeed you can show that suppose you start from some initial states, psi 0, then you send it to IIHT psi 0, right? And then you just let the time evolve, right? So basically you look at this, and you basically say, okay, what is the long time behavior of it? So you look at the average. Right, and for a very long time, this will be equal, right, in the limits, at least be equal to just the dephased version, right? So at least there is no degeneracy here, which usually there isn't. So this will be equal to right, so some dephased version where it's diagonal in the energy eigenbasis. Right, so this is just now what you can show actually using these ideas, right? If ETH is true locally, right? If you trace out most of the system, these are all the same, right? These are all like canonical states. So ETH, you can show that indeed, right? You look at this. If you trace out, we have like S, and the rest is like the Beth, right? You trace out the Beth. You look at I state of this form. Then after some convergence time, which is fast, right? So when T grows, this will go indeed to the reduced state of the thermal state there, with the same energy as the initial states. Right, so that's an interesting way of getting thermalization in quantum systems, right? The whole thing is pure, is isolated. There is no weak interactions, right? But this ETH ansatz gives us that locally the system will equilibrate, right? Which is, I think, interesting. So that's one. This just because that's a more like physics scenario where this idea that two quantum states which are really different from each other can be the same locally, and where it has important physical implications here, right? But in that case, the observables that we care about are local observables. I think are related to this result that we saw before. And indeed, many times, like in quantum chaos, people say, well, actually, our system is quantum chaotic. If you look just like random states, but with an energy constraint, right? Because we know energy is conserved, right? There is a time independent evolution, so the energy is conserved. They say apart from energy conservation, it looks just like a random model, right? And then you see the connection, right, of the two ideas. You can also look at a set of models which doesn't satisfy this. Then there is usually some kind of limitation there. Either they're integrable, if you perturb, they're not integrable, become chaotic, okay, or they can have some kind of localization and fails. And that's interesting too. But I want to tell you about that, but maybe I don't have time. Let me see. Maybe I'll leave that to you. So yeah, that's what I want to tell you about this. Okay, just to say again, right? That's it's a similar behavior to what we saw before. So now, what I was going to tell you about quantum chaos. You know, there are many open questions about this in terms of circuit complexity that would be nice to understand. For example, in this other phase, this many body localization phase that I didn't tell you, actually there's a very efficient way of creating any eigenstates, okay, as actually a matrix product states. That's what we know. From the MBL phase, you learn from Burak matrix product states. So because of localization, all eigenstates, they have in one dimension, they have a matrix product states parameterization. In the quantum chaotic phase, we would think that maybe it's the extreme case, right? Maybe actually all these eigenstates, it takes exponentially long circuit to create them, right? So that's which we know would make sense with this idea that they're really just like hard random states, but with some energy constraint put in, right? And this energy constraint shouldn't reduce the complexity too much, right? Because it's just like constraint about one particular observable H. But this we don't know how to show, right? So that would be an interesting problem to understand better the circuit complexity of eigenstates of this model. Here. Okay. So, you know, there is this, just recapitulate, because now I want to change gears again, one last time, the last like 15 minutes. So, I introduced this notion of circuit complexity, right, for states and circuits. The original motivation was to make sense of this black hole paradox, right, and just to argue that I didn't really show why we expect that to be the case, and we don't really know, but that's just because the interaction of the black hole is generic, we expect this decoding thing to have high circuit complexity, and there would be a way to solve it, right? Then I show you that thinking about circuit complexity is useful because it allows us to reduce the set of physical states that we care about, right? And we see that is a tiny subset. Then we also saw that this idea of like, you know, circuit complexity is related to local is related to distinguishability, right, of states from the maximally mixed states. And I saw an example where this is done, right, but now maximally mixed in some subspace of energy. That's just the content of this ETH, right, which is one of, like, I guess, frontiers of statistical mechanics at the moment, right, trying to understand ETH, the predictions, when it holds, and so on. Now I want to tell you one final application of circuit complexity in a different setting, which is like in condensed metaphysics, and maybe Burak mentioned already, which is for topological order. And that would be nice because then we can relate everything to entanglement again, and I think that's a nice way to finish. So again, it'll be very brief. Sorry, today is more like I went very slowly in the other lecture, so there was a lot of things I wanted to cover. So I just want to give you a flavor of these things in this class. So topological order is a new kind of quantum order, or not new, it's been around, right? It's part of physics, but people only started appreciating it more recently. And it's fundamentally quantum. It's property of systems at very low temperatures, or even like in the ground states, right? And it's the following. So you know, we want to classify phases, right? And the usual way to classify phases is just to look at some symmetry group associated to that phase, right? And to have some local order parameters associated to that phase. And for example, when there is a phase transition, the symmetry is broken, and this other parameter, it has a non-zero value suddenly, right? So for example, for a magnetic system, above the Curie temperature, it's non-ordered, right? So the magnetization is 0. Below the phase transition, the thermal phase transition, then suddenly this local order parameter, which is just the magnetization, it acquires a non-zero value, right? And this has been a successful framework, like Landau did the theory, worked very well. But then in the 80s, like people started studying, for example, the fractional quantum Hall effects, and they saw that they couldn't really understand the different, which appear like phases of the fractional quantum Hall effects, just by using this Landau classification. So there seems to be something else. That's the idea of topological order. Topological is just a misname, actually. You should think as, because many of these phases, we won't see this in detail, just want to tell you one aspect of this, but many of these phases, at very low temperature, they have a quantum field theory description of them, and you have to use a topological quantum field theory for them. That's why they name topological. And also, like, the degeneracy of the ground states depend on the topology of the of the lattice and so on. But anyway, what I want to tell you here is that the modern understanding of these phases is using circuit complexity, okay, but it's in a different way. So that's what I want to tell you, because I think that's nice, right? It's another way for a very physics concept where circuit complexity is important. So that is the following. Suppose we have, first, for topological order, we need a two-dimensional lattice. Okay, so we have qubits here. And then the idea is that we have some Hamiltonian here, right? Local Hamiltonian, like nearest neighbor or something like this. You can diagonalize. And then usually we're interested in the ground states, right? The lowest energy states, which is the state of the system at 0 temperature, right? And topological order is really a theory about, like, in which different phases this state can be, okay? Now let me define you what is a trivial phase. And this phase is the following. So suppose we start from some H0, okay, for which, so it has, right, so it's positive system definite, and this is the ground state. So the all 0 state is the ground state. Okay, so we have a trivial Hamiltonian where all spins are just products, right? And that's the ground states. So for example, an example of this H0 would just be sigma z's everywhere here, right? But it could be something else. And now suppose we have some H final, this H that we care about, right? Let me just call it HF for notation that we care about. And now we study a Hamiltonian, HS, which is, we just change from H0 to H final. Okay? And now suppose that we do this adiabatically. We do this very slowly, right? Then we start from this one, and slowly we change to this one. Then, right, if the gap doesn't close here, and we have to discuss this, but if the gap doesn't close, the adiabatic theorem works, and we expect, right, the physical properties of these two systems not to be too different from each other, right? But one will be like some dressed version of the other, right? So if delta this is the gap, okay? If the gap is the difference of the second eigenvalue to the first eigenvalue, so the second lowest to the lowest eigenvalue, this is the gap. Tells the energy scale of the problem, right? If the gap doesn't close, we say that H0, HF are in the same phase. And in particular, if H0 is like a trivial Hamiltonian like this, we say that HF is in the trivial phase. Okay, can be adiabatically mapped to a state which is completely product, where there is no entanglement at all there, right? Good. So this is like using Hamiltonian and so on. But the nice thing is that there is a similar characterization using circuit complexity, and this is what I want to tell you. What you can show, it's like kind of equivalent characterization of this class is the following. So we say that this psi 0, right, which is the ground state of the final model, is trivial if there exists a constant depth circuit V such that psi can be created by V applied to the trivial state, to the all zero states. Okay. The way to show the equivalence of this is just to basically, if there is such a path, you can do some kind of like throttle decomposition here, some circuit decomposition of this Hamiltonian evolution, and find the constant depth circuit. If there is a constant depth circuit, you actually build some H0 which does the job, right? But now that, okay, so what is a constant depth circuit? That I didn't tell you. So let's do a constant depth circuit in one dimension, although this will be in two dimensions. So in one dimension will be, we have our qubits, right? And now is the near now I require that, important. But I allow to do many in parallel. So in one round I can apply qubits 1 and 2, and at the same time qubits 2 and 3 and qubits 4 and 6 and so on, right? So I apply this round. As long as they don't touch, they can be done at the same time. Then in another round I apply now here, right? To qubits 2 and 3, 4 and 5 and so on, right? And then I apply another round, right? You know, so as many gates touch the same qubits, right? This is the depth, and now we say it stays in the trivial phase. Depth is constant if you can create it by a constant depth. Of course, we are in two dimensions. Two dimensions you have to visualize. Now this will be the qubits, right? The word line. So it will be like, you know, you apply some gates here, 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 right? In one depth. Then another one you apply them here and here, right? So similar thing, right? I guess. So draw on board. So now, the point is that you can show what is topological order. Topological order is Hamiltonians whose ground states are not trivial states. So whose ground state you can prove that to construct it you need linear depth there. So topological order meaning, well, meaning that you cannot do in constant depth and actually depth from many models, right? So what is the example? Is just is the ground states of what we call the toric code, right? Which is a commuting Hamiltonian dimension, 4-body interaction. So a very easy model. Maybe I won't have to write it, but show that, right, the ground state has this, you know, topological order, which means, right, that they have very rich entanglement, right? So to build them, you need this linear depth circuits. Whereas if I say this topological order, it's always you can adiabatically connect it, just apply a short circuit which creates it out of you know, a non-entangled state, a product state. And actually, there was recently a paper where they just did a computer search of all materials, like a large class of materials, and they found that surprisingly, a good fraction of them, like, I might be wrong, but I remember something on the order like 7% of them were topologically ordered, which was really surprising because it appears to be widespread than we thought. Yes.
In terms of a gap, is there any definition of topological order? Like, are you defining in terms of linear depth?
Yeah, so in terms of it will be topologically ordered if doesn't matter how, if you try to connect adiabasically to a trivial phase, you necessarily have to close the gap. That's what it means, yes. Yeah, the phases are classified up to, right, it's in the same phase, you can adiabasically go there without closing the gap. So if it's topological order, it will be outside, yeah, so the gap will have to close. Yeah. Okay, so now the last thing I want to do, and I won't have time to explain, but maybe you will check it. I want to write something about entanglement, right, just to finish, because this class had almost nothing about it. And the way it connects with topological order is that actually the effects in this thing of topological order, which is about, right, in a way, circuit complexity or about adjusting without closing the gap in the space of local Hamiltonians, there is a consequence to the structure of entanglement in the ground state. So suppose you have a state, psi, which is the ground state of a local model. Maybe Burak told you that. And let's look at some region X, okay? Then we expect very funny behavior of entanglement, distinguished behavior of entanglement. We expect this to be equal to some constant alpha times the size of the boundary of the region X, okay? Like this perimeter. And suppose this is like L, right? Up to some exponentially small correction in L. Scale of the region, right? Is the size of the region. So this is what we expect, right? And moreover, usually there is some translation variance in the states, so this alpha should be independent of the region, right? It's just a constant. Now, actually, there is another term. It's called gamma, and this is called topological entanglement entropy, and this is a manifestation of topological order. Okay, so if the state is trivial, psi trivial, gamma is 0, if psi topological order, then gamma is non-zero, and actually there is some expression for it related to the log quantum dimension of the model, but I don't want to get there. But this is a signature, right? So looking at the entanglement of the states of some region with the rest, there is an area law term. It is called area law term, right? So, that's, I think Burak told you, that's like what we expect for ground states of gapped models when there is a gap. But topological order manifests in the entanglement too in some constant correction, right? There is a constant correction to the area law, and that's related to the topological entanglement entropy. So this was first done more hand waving way and so on, but maybe the last thing I'm going to write. This now you can make this precise. You can show, for example, if gamma is 0, then there exists a constant depth circuit which creates the state. Now we can ask the other thing, right? So suppose that there exists a constant depth circuit that creates the states. Is gamma non-zero? And not in general. There are some counterexamples, right? So it appears to be one-sided, but this counterexample is special. Question is whether for, like, in the generic case, right? Suppose you have some translation invariance and you can perturb the gates a little bit. Is the reverse true? We don't know yet. Okay, so I think it's an interesting question. We expect to be true, but there is no proof yet. So this due to Kitayeb, this result. So I think that's an interesting connection, an interesting open question of combining many of the topics you saw here, right? So it combines circuit complexity with entanglement, and I think it's a relevant question. So I've been thinking about, don't know how to solve, but it's something nice to consider if you want. So yeah, today was just a a mixed bag of things, right? But I want to give you a flavor of the stuff I didn't really have time to cover. But that's a good point to. Thank you. Any final question, comments, criticism? Yes. Yeah. Oh no, but it's the fundamental entropy of the reduced density matrix, right? So X is this region, right? So you take rho X would be trace with respect to the complement of X, right, of the ground states, right? No, yeah, sure. So this is when X is less than like half system size. Indeed, there is a restriction. Yeah, thanks. Indeed, yeah, right. But then in that case, really, yeah, it will be independent of the shape of the region. Yeah. Yeah.
So for the topological order phase, the entanglement entropy grows slower than the area.
Yes. It's constant. It's like really a constant. Only depends on the topological properties of the model, like the anionic excitation and so on. Like.
Yeah. So what I wanted to mean is that, so I mean
This term is much bigger. Yeah.
is set,
Yeah.
right? It's the area.
Yes.
So has less I mean, so the entanglement is smaller for the topologically order phase.
Oh, it is. Yeah. It'll be, yeah. Exactly.
What is the reason?
Well.
Wouldn't we expect more entanglement?
No. Well, in a sense, they are more entangled if you think that they need this long depth, right, to create them, right? So they have this inbuilt long-range correlations in a way, right? But the way to think about that is usually these topological models, they have some global constraint here about, like some topological charge that has been conserved, right? And then this put the constraint of the inside and outside, and this restricts like the subspace where the reduced state can live here. And this leads to this thing here. So indeed, it's funny that you would think they should be more entangled because of topological order. They are more entangled, but in a different way, right? In the way of like circuit complexity, right? But in terms of just a bipartite measure of entanglement, it manifests, right? And yeah. Yes. You can think like that, yes. It's usually it's not very easy to find the decomposition, right? But indeed, you're right there. In the end, the output of the quantum algorithm is just indeed a sequence of gates which solves the problem. Yeah. Yes. No, it's impossible actually because you can show actually that take the lattice. Now consider three regions like this: A, C, and 2Bs. Now there is a measure I didn't tell you, but it's the conditional mutual information. I told you about the mutual information on the conditional, but it's always positive, right? It's always bigger than 0, and you can show that equals to 2 gamma. So actually there is a nice expression for gamma as the conditional mutual information, right, of two regions with like non-trivial topology. And this shows that it has to be, gamma has to be positive. Okay, any question? Other question? Okay, so that's it, thanks.